Alright, in this video we are going to talk a little bit about the electromagnetic spectrum as well as talk about wave properties in light equations. The electromagnetic spectrum is all of energy can be categorized and it falls somewhere on this spectrum. This slide has a lot going on. It tells you whether or not certain energy penetrates the Earth's atmosphere. It gives you the radiation type and wavelengths, which is nice because wavelength is a variable we are going to be talking a lot about in this video. Wavelength is given the Greek letter lambda, which is oftenly called upside down y, but it is the Greek letter lambda. Wavelength is how long a wave is from the top of one wave to the top of the next wave, if you will, or at any point, the same point in the wave. And it is typically measured in meters. So this would be a certain wavelength. And as we go this way, you'll notice that the wavelength is shrinking. Here is giving you just a bit of a scale. As far as here, a radio wave, the length of one wave is about as long as a building, all the way down to gamma rays, which the length of the wave, we're just talking nuclei of atoms now. The frequency is how fast the wave is traveling, and we'll talk more about that on the next slide. But frequency is given the Greek letter nu, which quite honestly I agree it looks like a V, but it is nu. And then down here it's a bit of extra information, but it was on the slide. It gives you the temperature at which the radiation is the most intense. One thing that I wanted to point out is here is our frequency is getting higher and higher and higher. The radiation wavelength is getting shorter and shorter and shorter. So as frequency goes up, wavelength goes down. And that relationship is always true. So let's clear that and go to the next slide. So light and energy. Here's just a nice snapshot of a wave, and we're not going to change its wavelength at all like what was happening on the previous page. So wavelength, here's a nice example of what it actually is measuring from the height of one to the next wave. We have a height of a wave, which is called the amplitude, as well as the trough, that's the bottom. We're not going to you don't need to memorize this terminology or anything. It just gives you a little bit of background information on waves. So wavelength is how long it is. Frequency, if we were to draw a point in time, maybe, there we go. If we were to draw a point in time and count how many waves, how many heights of the wave pass per a given unit of time, per second is what it's usually counted as, that would tell you the frequency. So frequency is similar to speed in this instance. Down here we have our two main concepts. The speed of light is a constant value. It's actually 3 times 10 to the 8 meters per second. So how fast light travels is equal to the length of the wave times how fast it's going. So as the wavelength gets longer, since it's an indirect relationship, the frequency must get shorter. And then the second main concept is saying that energy, which we actually give it just a variable letter E, thankfully that one makes sense, is directly proportional to our frequency. And our frequency was up here, it was how many waves would pass through a given point per second. So energy is directly proportional to the frequency. So that means if the wave starts going faster, well, for one, if it's going faster, the wavelength is going to get smaller, but the energy goes up. So our high energy waves are the ones that travel fast, and they also have a short wavelength. So conceptually, that gives you some background as far as waves. From a chemistry perspective, we actually end up doing some math associated with that, if that's not surprising to you, with light equations. And this fundamentally helped us come up with the current model of the atom, and electron placement, which we're going to start talking about very soon. So we have two light equations. The first one involves the speed of light, And the speed of light is equal to the wavelength times the frequency, which we have just mentioned on the previous slide. So the speed of light is measured in meters per second. It's a constant value. It's always going to be this number. Lambda is the wavelength that's measured in meters. The frequency is measured in hertz, which by definition means 1/2. So for an example problem, to find the frequency of light, frequency was nu, when the wavelength is 1.2 times 10 to the 8th meters. So we're looking for nu, and we're given wavelength in C. Well, we always have it. So C equals lambda nu, where C is 3.00 times 10 to the 8th meters per second, equals our wavelength, times nu. Now we just need to solve for nu, so we're going to divide both sides by the wavelength to get them to cancel out over there. And over here we are dividing scientific notation. So when you're dividing scientific notation, just as a quick reminder, we divide the number portion, so 3 divided by 1.2. If you do that out, you end up getting 2.5. And conveniently enough, since our exponent over here is the same, this just cancels out. However, had it not been the same, you end up subtracting exponents. So let's say this was a 7, you'd end up doing 8 minus 7. So you would write down 2.5 times 10 to the 1. Fortunately, it just cancels out for this problem. So 2.5 meters per second, actually, is nu, except it's not meters per second. The units are hertz, and let's talk about that. So we had meters per second here, and we divided it by meters. So here we're essentially dividing a fraction. So whenever you're dividing a fraction, you take the reciprocal and multiply it. So meters per second times 1/meters allows meters to cancel out, and you end up with a unit of 1/seconds, which by definition is hertz. So I don't care honestly if you write 1/second or 1/s or hertz when you are writing the units associated with frequency. It doesn't matter to me, as they all boil down to being the same thing. Alright, so for our last light equation, it's concerning energy. Energy is equal to another constant. In this case, it's called Planck's constant times the frequency. So energy is measured in joules. This should be familiar to you based on all the work we've done so far. Planck's constant is a constant value, and it's not written on your slide. It's 6.626 times 10 to the minus 34. The units associated with that are joules times seconds. So 6.626 times 10 to the minus 34 joules seconds. Frequency is still nu, and that's measured in hertz. So for our example problem, we're looking to find out how much energy light has if it has a frequency of 450,000 hertz. So energy equals h times nu. H is this value, always. Times the frequency. The frequency can sometimes be given to you in kilohertz, because quite honestly, to write out 450,000, it's much easier to write 450 kilohertz, and you would need to convert that to hertz to use it in this problem. So with multiplying a number, one of them in scientific notation and the other one's not, you end up multiplying this number portion times this number and just carry the times 10 to the minus 34. So 6.626 times 450,000 ends up being a pretty large number. It's 2,981,700 and carrying times 10 to the minus 34. And you can adjust this for scientific notation, or you can leave it as it is. It doesn't matter to me. As far as units, joules times seconds times hertz, which by definition is 1/second. So we're multiplying a joules times second times 1/second. Allow seconds to cancel out. So your units for energy are in joules, which they should be.